Hi there, this is your favorite non-Indian math channel, and I have a pretty cool limit problem for you. So, well, it's not really obvious what the answer is going to be. Is it going to be 1, 0, infinity? Well, the answer is none, okay? And so the first way is the boring one, okay? Uh, they could tell us that, for example, if we name this top part Sn, okay? They could tell us that 2 square root of n is, sorry, I also have minus 2, is less than Sn, which is less than 2 square root of n minus 1. Well, they could either just give it to you, or they could ask you to also show this is true, and then you could just divide all sides by square root of n, and you would say, okay, this limit is going to be equal to 2. But this is a boring one. Why? Because they gave us the solution, okay? There's nothing interesting about this. But now we're going to learn how to show this like a man, okay? We will find a similar inequality. We're gonna find bounds for Sn from scratch. Okay, so let's see how we can do it. So I'm saying my Sn is equal to k is from 1 to n, 1 over square root of k. So how can I find bounds for this? Let's graph 1 over square root of x. It would look like this. We can also define it for negatives, but so I have, let's say, fn is 1 over square root of n, and fx is 1 over square root of x. Okay, so we are considering these two. And what can I do is that maybe I can just look at the values of, let's say, from k and k plus 1. Maybe if I look at the integral from k to k plus 1 fx, either this would be greater or less than fk. Would this be true? How can I see that? Well, one of them is going to be true, and we will see how. So I'm deleting it, and so this integral, let's call this S, okay? So this is an area, or let's show it like A. So this integral is equal to this area. And actually, here I'm going to also introduce you intermediate value theorem for integrals, but you don't really need to know it. It's quite intuitive. The definition is quite intuitive. So I'm gonna draw this same area, okay? So this is the area that I have, and intermediate value theorem is saying you that you have a midpoint, let's say C is here, it doesn't have to be at the middle, that if you take this C as height and same width, imagine this is same width even though it doesn't look like so, okay? These width are same, okay? Here it was 1, so this is also 1. These areas are gonna be same, okay? We always have such C between this k and k plus 1. Let's say it's here, okay? And this height is fc. Let's show it like fc. Okay, cool. So what does it mean? Is that I can find the c such that this area is equal to fc times 1, since the width is 1, but we don't need to write it, okay? So it's just fc. And so my goal was to compare this with k, fk, and I know that since this function is decreasing, the sequence is also decreasing. So fc is actually less than fk. Boom, we found the upper bound. So what does it mean is that, so to find Sn, we need to add all of the k's from 1 to n, okay? So if I do that on this side, from k to 1 of fk, this thing is just gonna give me Sn, okay? Because fk is just 1 over square root of n. Sorry, 1 over square root of k, and this is how I defined Sn. And on this side, So I'm adding all of the k's from 1 to n, and I know that I can just combine integrals. So this thing is gonna be bigger than, so this integral is less than. So I'm adding k from 1 to n, so this integral is gonna be from 1 to n. And it's gonna be fx. I can directly write it's 1 over square root of x dx. I also have dx here, okay? So if you noticed, we found that this integral, which is totally easy to find, this antiderivative, this is an lower bound for Sn. So let's do a similar thing and find upper bound. So if I go back here, and so I found that if I pick a c value that bigger than c, I found a lower bound. So if I pick a c value here, okay, so this means that if I integrate this thing from k minus 1 to k, okay, oops, sorry. So if I integrate this thing from k minus 1 to k fx dx, I'm going to be able to find another c between here. Let's show it here, okay? Let's say this point is fc2. So I have a midpoint. It doesn't have to be again at the middle. I have a point between k minus 1 and k. This is exactly the same logic. That I can find a c2 such that this area is going to be equal to f of c2 times 1. So it's just fc2. And so since I know that this function is decreasing, f of c2 is greater than f of k. And if I again just add all of the k's from 1 to n, and I'm just swapping inequality, k from 1 to n, my fk, let's directly write it, which is equal to Sn, this is less than, so I'm adding all of these integral from 1 to n. If I put 1, it's going to be 0. If I put n, it's going to be n, and my function is 1 over square root of x dx. And this is my second bound. Look what we have found. We found that our Sn is bounded above with this integral and bounded below with this integral, and they're both same integral, okay? So we're almost done. Let's evaluate this integral. Well, it's pretty easy. 1 over square root of x dx. So I know that if I differentiate square root of x, I'm gonna get 1 over 2 square root of x. So if I just multiply it by 2 and divide it by 2, this is gonna be equal to 2 square root of x plus c. So I'm just wrapping it up. So I found that Sn is less than, so I found that from 1 to n, it was 1 over square root of x. Sorry, here I added all of these k's from 1 to n, so this upper bound should be n plus 1. Okay, it's a bit nuanced, I'm sorry about that, but nothing is going to change. So I found this integral from 1 to n plus 1, 1 over square root of x dx is less than Sn, and the other inequality is that from 0 to n. Well, I noticed it because from this distance wasn't n, okay? This distance is n, this one is not. Okay, so I noticed there is a mistake. So I have 1 over square root of x dx. And so I found that this integral is just 2 square root of x. So this integral is going to be 2 square root of n plus 1. And if I put 1, it's going to be minus 2 less than Sn less than 2 square root of n minus 0. Okay, so we found a pretty similar bounds for Sn. Let's go up and compare them. Okay, so this was the given in the first way. That sucks. Okay, and my way, I found that 2 square root of n plus 1 minus 2 is less than Sn, which is less than 2 square root of n. Well, I don't know how could I find exactly the same thing. There's no point doing that. And so let's also compare this. Well, this for lower bound, this lower bound is bigger. Okay, so this is a better approximation on this part. But on this side, this is literally just one less. Okay, so this part is better approximation for this. Maybe I could just combine both of these, but there's no point doing that. Okay, so I proudly got this answer, and I'm gonna use this. So now, I found an bounds, I found lower and upper bounds for Sn. So now I don't know the answer if I just squeeze this thing. Okay, so I know that Sn 2 square root of n and 2 square root of, let's write it a bit more left, 2 square root of n plus 1 minus 2. So in the question I have Sn over square root of n. So if I just divide all sides by square root of n, this right side is literally just 0, literally just 2 for any values of n. And so now, if I can show that this left-hand side would go to 2 as limit as n goes to infinity, then I could say that by the squeeze theorem, this limit is going to be equal to 2. Okay, so again, sorry. So my limit, if I can show that limit as n goes to infinity of 2 square root of n plus 1 minus 2 over square root of n, if this is equal to 2, I'm done. And it indeed is. Okay, so I can just separate this thing. I can write it as limit of 2 stuff because I know both of these limit exist. Okay, so it's 2 square root of n plus 1 over square root of n. And if I separate this limit, minus 2 over square root of n, if n goes to infinity, this thing is just 0. Okay, so I'm not going to write that. This limit is n goes to infinity. Here I know that this limit exists. Okay, it's why I could separate them. If this limit didn't exist, I couldn't separate them. So I have 2 n plus 1 over n. So square root of x is just continuous. So I can say just if n goes to infinity, this limit is going to go inside. This is 1. The inside of square root is 1. So it's going to be 2 times square root of 1, which is equal to 2. So let's go back up. I found that this thing is literally just 2. So of course this thing is just going to converge to 2 as n goes to infinity. And I found that this thing would converge to 2 as n goes to infinity. So I can say by the squeeze theorem, this Sn over square root of n, which was given in the question, this limit exists. Okay, this is the first result that we get from this squeeze theorem, and it's equal to 2. Okay, and equal to 2. So this is our answer.